All right, kiddos. So what we're going to learn about today is completing the square and taking square roots. um, Here's our EQs. Why do quadratic equations have two solutions or roots? How can we use square roots to solve quadratic equations? What's it mean to factor by completing the square? And how can we use factoring by completing the square to solve quadratic equations? So we're going to learn a new way of factoring, and hence a new way of solving quadratics. So first, let's talk about what we're getting at with square roots. Okay, so if you look back at our EQs, how can we use square roots to solve quadratic equations? So that's easily our more intuitive algebraic way to solve a set of quadratics. So here, for example, we've got x squared equals 20. So let's look at that one first. Right, so common sense tells us all we would do is take the square root of both sides, right? So what we end up with is x equals the square root of 20. Well, we can't only say that, right? Because if you remember back, I showed you guys an example. So the x squared equals 25. If I take the square root of that, well, our answer would be plus or minus 5, right? That's because 5 squared equals 25. Which is also equal to negative 5 squared, right? So any square will always have two roots, or in the case of a quadratic, we'll call them solutions. Two roots or solutions. And we'll learn more. They really mean the same thing for all intents and purposes. So instead of just writing square root of 20, there's a number of ways we can express this. We can do like what we've been doing and say x1 equals the square root of 20, x2 equals negative square root of 20, or we could just say x equals square root of 20, comma, negative square root of 20, or we could say x equals plus or minus the square root of 20, right? Now, let's talk about the square root of 20. That's still not our simplest way to express this answer. Okay, so we could say plus or minus the square root of 20, but if you remember back from geometry, we can factor this radical expression of square root of 20. We can say that this is the square root of 4 times 5, right? And if you remember the laws of radicals from geometry, we can say that it's the square root of 4 times the square root of 5, and the square root of 4 is 2. So we can say that the square root of 20 is the same thing as 2 square root of 5. So instead of saying plus or minus square root of 20, we're going to say plus or minus 2 square root of 5. And this is how I would want you to express your answer. This would be your fully simplified solutions, right? So let's move on to another example. And again, all we're doing here is getting x by itself. That's all solving equations is, whether we're using factoring or not. The entire idea is to get x by itself. The only difference here is we've got quadratics, which means what? Well, we're going to have two solutions every time, right? So looking at this one now, 3x squared equals 32. Well, we've got an extra step to throw in there. So to get x by itself, we're going to have to divide by 3 on both sides. That's going to give me x squared equals 32 over 3, right? And if we continue, take the square root of both sides, we're going to have x equals plus or minus the square root of 32 thirds. Again, we can simplify this radical expression even further. Okay, another law of radicals that we talked about was the quotient law. So the one we saw earlier was the product law. This one's the quotient law because we have a quotient. We have a number being divided by another. Okay, so we can rewrite this as square root of 32 over the square root of 3. All right, remember, we did this in geometry. This isn't new. Anyway, we can go ahead and factor the square root of 32 the same way we did the square root of 20. We can say that we've got square root of 16 times 2 over the square root of 3, we can go ahead and say the square root of 16 is 4, so we've got 4 square root of 2 over the square root of 3. And you'll remember something also from geometry. We've got a radical expression in the denominator of a fraction. That's bad. That means we have an irrational denominator. That's no bueno. And the way we get rid of that is multiply by the number we want to go away on top and bottom. Okay, again, not new. And what we're going to end up with is 4 square root of 2 square root of 3 over 3, right? Because this here would simplify down into the square root of 9, which is equal to 3. So that's where we got that from. And with that same logic, this guy right here, square root of 2 times square root of 3 is equal to the square root of 6. So we would say our answer is 4 square root of 6 over 2. This would be our final answer. So we would say plus or minus 4 square root of 6 over 2. And actually, the 4 and the 2, we can reduce that even further. So let's go ahead and do that before I go off saying that's our final answer. They're both divisible by 2. So we can say that our answer is really just 2 square root of 6. Okay? Now let's continue. Whoops, let's get too far ahead. Forgot where I was at. So now let's talk about solving quadratic equations. So we simplified a few already. Let's do a few more examples. So again, our objective here is to get x by itself. And we're just using common sense algebra here right now. Okay, no factoring or anything necessary, although we could. This is technically a difference of squares, right? So one way we could solve this is using common sense. So let's go ahead and do that first. So we're going to end up with 9x squared equals 49 because we added 49 to both sides. Divide by 9 on both sides, and we get x squared equals 49 over 9, right? Take the square root of both sides, and we get x equals plus or minus the square root of 49 over 9, which is equal to plus or minus the square root of 49 over the square root of 9, right? That's our quotient law of radicals again, which is equal to plus or minus 7 over 3, meaning x1 is 7/3 and x2 is negative 7/3. Right? Now, we also could have treated this as a difference of squares. Okay, we could say that this is 3x all squared minus 7 squared, which by our little difference of squares formula, if you remember, a squared minus b squared is equal to a plus b times a minus b. So we can go ahead and rewrite it that way, and we'll get 3x plus 7 times 3x minus 7 is equal to 0, right? Because again, we've got this set equal to 0 originally. We're just looking at its original form here. Okay? And if we solve each one, so x1, x2, we can say that x1, if we subtract 7 from both sides and then divide by 3, that's equal to negative 7/3. Same thing we got here. And if we do the same thing over here on this factor for x2, we'll get that x2 is equal to positive 7/3 because we add 7 and then divide by 3. Right? And you'll see we get the exact same final answer. And I don't know why that stupid thing just did that. There we go. Okay. So let's look at a couple more examples. These next ones, we're not going to be able to use factoring. We're going to only be able to use just basic algebra. So, number 2, 25x squared minus 7 equals 0. Well, now we can't use difference of squares, even if we wanted to, right? So we're just going to use old-fashioned get x by itself algebra. Add 7 to both sides, divide by 25 on both sides, take the square root of both sides, and we get that x is equal to plus or minus the square root of 7 over 25. Use the quotient law of radicals. We're at plus or minus the square root of 7 over the square root of 25. Square root of 7 can't be simplified any further, so that stays square root of 7. Square root of 25, however, is going to be 5. So our answer would be plus or minus square root of 7 over 5, or we would say that x1 equals the square root of 7 over 5. Okay? So let's go ahead and move on to number 3. This will be our last example for this little bunch right here. And then you can see below we've got a little bit more complicated of examples we're going to work through. So we've got 5x squared is equal to 16. Again, we can't do anything cute like factoring, because even if we do set this equal to 0, so 5x squared minus 16 equals 0 by subtracting 16 on both sides, I do not have a difference of squares. I don't have a GCF between them, so I can't use factoring. All I can do, as we said, is just use good old-fashioned algebra. So all I'm going to do is divide by 5 on both sides. Then I'm going to take the square root of both sides. Now, forgot to put plus or minus, so that's going to give me plus or minus, so the square root of 16 is 4. Square root of 5, well, we don't have a nice cute square root of 5, and also we cannot have an irrational denominator, so we're going to have to rationalize the denominator. So we're going to multiply by the square root of 5, top and bottom, and that's going to give me 4 square root of 5 over 5. Now, anytime you get a set of solutions, and I should put plus or minus, but anytime you get a set of solutions where you have to rationalize your denominator, that means your solutions, so both my two solutions, right, are not rational, aka they are irrational. I can't spell. Irrational. So our solutions are irrational. And our solutions in this case would be x1 equals positive 4 square root of 5 over 5, and x2 is equal to negative 4 square root of 5 over 5. Okay, so my two solutions here are irrational because I had to rationalize my denominator right here. When I had to rationalize this, that told me that my solutions were irrational solutions. Okay, so keep that in mind. Okay, so let's move on to our other little set of examples down there. These are going to be a little bit more difficult. So number 1, I've got 2 times x minus 3 all squared minus 5 equals 0. So these look a little bit different, but again, the idea is the same. Obviously, by looking at this, you know, we can't do anything cute like difference of squares. We can't do any kind of factoring whatsoever. So all we can do is get x by itself. So we're going to start by just adding 5 to both sides. And then we're going to divide by 2 on both sides. And then we're going to take the square root of both sides. So that's going to give me x minus 3 is equal to plus or minus the square root of 5 over the square root of 2. X still isn't by itself, so we can't really stop and say that we have our two solutions just yet. So we still need to add 3 to both sides, right? Because we've got that minus 3. So we're going to go ahead and just say x is equal to 3 plus or minus, and I say 3 because it was a positive 3, right? I had to add 3 to get rid of it. Anywho, we're going to say x is equal to 3 plus or minus square root of 5 over the square root of 2. Again, we have an irrational denominator, right? Right here. That's irrational. We can't have that. So we're going to have to rationalize. And if we have to rationalize our solution, again, that means that we have irrational solutions. Okay, so we're going to have x is equal to 3 plus or minus the square root of 10 right? Because square root of 5 times square root of 2 is going to give me square root of 10 over 2. Okay, so we would say x1 is 3 plus square root of 10 over 2, and x2 is equal to 3 minus square root of 10 over 2. And those are my two solutions, and they're irrational because I had to rationalize my denominator of my solution set. Okay, so let's look at our second example. Let me erase all of this as best as I can. So I've got 4 times x plus 5 all squared minus 49 equals 0. Again, just solving for x, add 49 to both sides. Divide by 4 on both sides. Take the square root of both sides. And we can go ahead and simplify that. So we can say the square root of 49 is 7, square root of 4 is 2. We still don't have x by itself because of that plus 5. So we need to subtract 5 from both sides. So we're going to say that x is equal to negative 5, plus or minus 7 over 2. Okay, because again, when I took the square root over here, that should be plus or minus, that should be plus or minus, right? So that would be my solution set there. I didn't have to rationalize or anything like that, so these solutions are going to be rational. Okay, there was no rationalization that I had to do in the denominator, right? So that means my solutions are rational. So x1 is negative 5 plus 7 halves. x2 is negative 5 minus 7 halves. Right. Number 3, we've got 3 times x minus 2 all squared minus 16 equals 0. So start getting x by itself. Add 16 to both sides. Divide by 3 on both sides. Oh, actually wrote the 3. Take the square root of both sides. Okay, and we see right here, we're going to have irrational solutions. Okay, because we're going to have to rationalize. So the square root of 16 is 4, right? And then we have to multiply that by the square root of 3. So we've got 4 plus or minus 4 square root of 3 over, and this guy underneath is just going to be 3. And we still don't have x by itself. We still have to get rid of that minus 2. So we're going to add 2 to both sides. That's going to give me x is equal to positive 2 plus or minus 4 square root of 3 over 3. So my two solutions, x1 is equal to 2 plus 4 square root of 3 over 3. And x2 is equal to 2 minus 4 square root of 3 over 3. And these would be my irrational solutions. Again, they're irrational because of what happened here, right? I had to rationalize, so that meant my solutions were irrational. Okay, and one more example. So I've got 5 times x plus 1 all squared minus 8 equals 0. Add 8 to both sides. Divide by 5 on both sides. Take the square root of both sides. And our solutions are going to be irrational again, because we're going to have to multiply by the square root of 5, top and bottom. And that is going to leave me with plus or minus square root of 40 over 5. We can simplify the square root of 40. We can factor out of that radical. So we can say that this is 4 times 10. So this would be 2. Here, let me write it out. Okay, so that means I've got square root of 4 times the square root of 10. That's going to change to just 2 square root of 10. So I've got plus or minus 2 square root of 10 over 5. X is still not by itself. I still have to get rid of that plus 1 by subtracting 1 from both sides. So I'm going to have x equals negative 1 plus or minus 2 square root of 10 over 5. So my two irrational solutions will be x1 is equal to negative 1 plus 2 square root of 10 over 5, and x2 is equal to negative 1 minus 2 square root of 10 over 5. Those would be my two irrational solutions there. Okay, so pretty straightforward there. Now let's talk about a different kind of factoring that we're going to need to know how to do. And this actually is going to lead to something that's called the quadratic formula, which we'll get into in the next lesson. But anywho, completing the square is a different kind of factoring, and what it amounts to, or basically what it derives from, is what's called perfect squares. Okay, and let me use a different color here. So what we've got is x plus 1 all squared. We're saying that it's equal to x squared plus 2x plus 1. And the reason for that is when you FOIL this out, like so, you're going to end up with x squared plus x again plus 1. And combine like terms, x squared plus 2x plus 1, right? So now let's look at another one. Well, let's look at this guy here. So x plus 3 all squared is going to equal this. And again, that's because when we FOIL it out as x plus 3 times x plus 3, we're going to arrive at this guy here. So x times x squared, 3 times x, plus 3 times x, plus 3 times 3, which is 9. Combine like terms, and we get what we should have gotten, this guy right here. Now, what does this all mean? Well, basically, when you have something that's a perfect square, it's going to look like this, right? So you're going to have, let's try and picture this, and actually, I gave myself room on the bottom for a reason. I don't know why I'm trying to draw it there. So what you've got when you have x plus b squared, like this, you always end up with x squared plus 2bx plus b squared. Okay, the 1, right, became a 2, and 1 squared is 1. The 3 became a 6, and 3 squared is 9. So that's the pattern, the generalization that we can make there. And when you break this down, you end up with, if you break this down geometrically, I mean. So this guy here would be the x squared, meaning that this side of the square is x, and this side here is also x, right? And you would add that to 2 times bx. Okay, well, what is that going to look like? So let's go back to this guy here. Okay, x plus b all squared. So let's break it down starting from there first. So basically what you end up with is, this is your x squared. Okay, and let's say here in pink, that's the length of b, right? And this guy, obviously, length of x. And here we would have another one because we have 2bx, right? So this guy would also be b, meaning that this whole side here is equal to x plus b, and this whole side here is x plus b long as well, right? Well, what about here in this little corner? Well, this would be b, and this would also be b in length, making this little guy be b squared. And here in pink, I forgot to label, so the area to this guy would be b times x, this guy would be b times x. And what you end up with x squared plus 2bx plus b squared, right? And that's exactly what I've got here, okay? That's whenever you have a perfect square. Whenever you have a perfect square, you can express it in this way here, geometrically speaking. Okay, well, let's talk about if we don't have a perfect square. So what we have here, if I have x squared plus bx, what we have here is like an incomplete square. What could we add to it? We could add some constant to it. What could we add to make it complete? Well, let's look at the geometry again. So let's start with what we've got. So we've got x squared, oops, right? Because its area is x times x, and we're adding b times x, meaning one side is b long, and here, let me color code. One side is the length of x, and another side is the length of b, right? And actually, here, let me draw that a little wider, just to prove a point a little bit better. Okay, so that means I've got x plus bx, right? So let's try and form this into a square. So what if I took this bx and cut it in half, right? If I cut it in half and placed it around, so here's my x squared again. Right, and if I just kind of took these little half pieces here, so this side length is equal to 1/2 of b, right? And same thing over here. This side length is also equal to 1/2 of b. Okay, so what I've got is 1/2 of b times x, 1/2 of b times x, and I'm left over with a little missing piece right here that would complete my square. We'll just call that the square completer. That's what's missing. If I blow that up larger, okay, this side here, obviously, is the same length as this side here. So that would be 1/2 of b, or b over 2. This side here, obviously, is this long here, which is also b over 2. So the area of this guy, what it's equal to, is b over 2 all squared. So I can complete this square by just adding in 1/2 of b all squared, right? So geometrically speaking, it's pretty straightforward, right? Well, what about algebraically speaking? Algebraically speaking, it seems simpler, but there's something we have to take into account first. So let's start here. I've got x squared plus 8x plus 1, right? This is not a perfect square. We can't use AC grouping here. We can't use anything cute, right? So what ends up happening, if I draw a picture, so this is x squared. That means this is x, And what I've got over here is 4. This is x, so this guy inside is 4x. Same thing over here. This is 4, right? So each one of these is x plus 4 long. Okay, and this guy in here would be x, so this would be 4x as well, giving me a total of 8x like I'm supposed to get, right? But I've got a little missing piece in here. Okay, and if we go back to this generalization that we've got, if I just take b and divide it by 2 and then square it, I should be able to complete the square. Okay, and if we do that, so let me blow this guy up, right? This guy here would be 4x, right? This guy here would, or not 4x, I'm sorry. That guy there would just be 4. And this guy here would also be 4, giving me 16 to complete my square. So basically, what I can do is say that x squared plus 8x plus 1 is equal to, if I wanted to complete the square, it's equal to x squared plus 8x plus 16, but I also would have to say minus 16, right? Because you can't just pull a number out of nowhere. So basically, we're adding nothing. We're adding 0, which is okay. It's okay if we add 0. That's perfectly algebraically sound. And I cannot forget the 1, this one right here. Okay, so what I'm going to do next, I'm going to group. And, well, what do I have? I've got x squared plus bx plus b squared, don't I? If I do AC grouping, so AC would be 16. The factors of 16 that add to b would be 4 and 4. And that gives me x squared plus 4x plus 4x plus 16, right? And group and factor, you're going to factor out an x here on the left. You're going to factor out a 4, plus 4 there on the right. And you're left with x plus 4. And guess what you're going to get? Common factor of x plus 4 gets factored out, and you're left with x plus 4 again. Okay, so doing the AC grouping obviously leads to the realization that this is a perfect square now. So we can go ahead and rewrite this guy as x plus 4 all squared, the perfect square, right? Minus 16 plus 1. Just combine like terms where we're able. So x plus 4 all squared minus 15. So this guy right here, we just factored it into a perfect square. Well, the sum of a perfect square and a constant. Okay, so let's try this again, except without so much drawing this time. We don't need to do all the drawing. I'm just doing that to prove where this is coming from. Okay, so let's use blue this time. So I've got x squared plus 12x minus 9. Oops. Okay, so this is not a perfect square, and we can't factor it in any other kind of way. So all we're going to do is treat it like we did before, like if it was x plus bx. So all we're doing is trying to complete the square, and the generalization we came to was to complete the square, all you've got to add in is b over 2 all squared. So our b obviously is equal to 12, b over 2 is equal to 6, and b over 2 all squared is equal to 6 times 6, which is 36. So if we just add in a 0, effectively, so x squared plus 12x plus 36. That completes our square, but we also have to say minus 36, and we can't forget the minus 9. Okay, this guy now is a perfect square because we've got x squared plus bx plus b squared. Okay, or actually I should say, let me back up. X squared plus bx plus b over 2 all squared. Okay, and we know that that's the case from our little geometric proof we did earlier. Anyway, so we can go ahead and rewrite it as x plus 4, whoops, not 4, 6 all squared. Minus 26 minus 9 would be 45. So our answer here, x plus 6 all squared minus 45, right? Now let's make another generalization really fast before we move on. Our generalization being that if you have a complete, or if you have a perfect square, let me go back here, a perfect square, or if you're trying to complete the square rather, all you really have to say is, I'll use this one, all you'll really have to say is that x squared plus bx plus b over 2, right, and then plus some constant c, and that would be b over 2 all squared, that's equal to x plus b over 2 all squared plus c. Okay, so let's keep that in mind on this one. Oh, we've got a problem. We haven't seen where we have an actual a term, and this time we have an a term. Okay, so let's go ahead and look at that really quick, and then we'll back up and just kind of generalize. All right, so 5x squared plus 10x plus 15. Okay, when we're factoring by completing the square, we cannot have an a term. Our a term needs to just be 1. In this case, it's not. So we need to divide everything by 5. Okay, or we need to factor out the 5. And it works out this time because 5, 10, 15, they all have a GCF of 5 anyway. So it doesn't really hurt us. So let's go ahead and factor out the 5. So we're going to end up with 5 times x squared plus 2x plus 3, right? And if we want to complete the square of what's in here, we can definitely do that. We can go ahead and establish that b is equal to 2. B over 2 is equal to 1, and b over 2 all squared is equal to 1 times 1, which is 1. So that's going to be our square completer, right? Again, this guy right here, b over 2 all squared is our square completer. So all we're going to do is add that right into here. So we're going to say that we've got 5 times x squared plus 2x plus 1, right? And add an extra set of parentheses there just for some grouping, and we have to do a minus 1 to balance what we've done, because we can only add 0. We can't just add something out of nothing, right? Okay, this is going to factor out this way, right? So we're going to end up with, well, before I say equals anything, let's figure out what this is going to be. This is going to end up being x plus 1 all squared. And then we can combine these like terms. Minus 1 and plus 3 is going to combine to give me plus 2. Right? And we can go ahead and distribute the 5 in here if we would like. And that leaves us with 5 times x plus 1 all squared plus 2. Oops, not plus 2, plus 10, because we have to distribute the 5 into the 2. What am I, stupid? All right, you get the idea. Okay, so now let's take what we've learned about completing the square and apply that to solving equations. Okay, so Let me check where I'm at for time. I am at 39 minutes, and that is brutal. Okay, so this video is extending on pretty long. So let's go ahead and generalize completely what this process is. All right. So establish what b over 2, and b over 2 all squared is. Then you're just going to plug into that formula that we had, right? So you're going to have x squared plus bx plus b over 2 all squared. That is equal to, so when we actually complete the square, and we can go ahead and include the c, I guess, on this side as well. That is equal to, so this right here factors into, oops, why did I do that? Factors into this. This becomes this because this is a perfect square, okay? So always keep that in mind. That's going to save you a lot of time. And then obviously, of course, if you want to, you can FOIL this. If you FOIL this, you should get back to this if you did everything right. Okay? So now we're going to go ahead and start solving quadratic equations by completing the square. Okay, and that's going to be the last thing on this video. So this video is pretty long, but it's for a reason. Okay, so let's start with number 1. We've got 2x squared plus 12x equals -5. Okay, so what we need to go ahead and do, we don't want that a term, right? So we need to make it go away. So that means we're going to have to divide by 2. And we'll go ahead and just divide by 2 on both sides of the equation instead of factoring out the 2. So when we do that, that's going to leave us with x squared plus 6x equals -5 halves. Okay, let's go ahead and complete this square then. So b is 6, b over 2 is 3, and b over 2 all squared is 3 times 3, which is 9. So to complete the square, x squared plus 6x plus 9, and remember, so again, algebraically, we need to be adding 0, right? To make this algebraically sound, we could say it's plus 9 and minus 9, right? We could say it's plus 9 and minus 9 equals -5 halves. Or you could just think of it as, well, what I do to one side, I do to the other, right? So you could go ahead and just say that you're going to add 9 to both sides. Okay, however you want to do it. I'm going to go ahead and do it this way because it's going to save me some steps. So we're just going to say -5 halves plus 9. And again, I'm treating it, as what you do to one side, you do to the other. So this is now a completed square. I'm going to have x plus b over 2, which is 3, all squared. This factored into this, right? This factored into this. And that's equal to -5 over 2 plus 9, which let's go ahead and make this into a common denominator. So this will be 18 over 2. And we're going to have, so -5 plus 18, that's going to give me positive 13 over 2 is equal to x plus 3 all squared. Take the square root of both sides. So we're going to have plus or minus square root of 13 over the square root of 2. And we're going to subtract 3 from both sides. We're going to get x is equal to -3 plus or minus the square root of 13 times the square root of 2 over 2. I had to rationalize there. And here, let me back up. I skipped a step. I don't want to confuse you. So square root of 13 over the square root of 2. Okay, so this is an irrational denominator. So that means my solutions are irrational. Okay, so I'm going to multiply by the square root of 2 on top and bottom. and I'm going to have negative 3 plus or minus the square root of 26 over 2. And these would be my two irrational solutions. So x1 would be equal to negative 3 plus the square root of 26 over 2. And x2 would be equal to negative 3 minus the square root of 26 over 2. Right? All right. Let's do that again. Oops. So looking at number 2 now. There's got to be a better way to erase. Looking at number 2 now, 4x squared plus 16x minus 5 equals 0. Okay, so all I got to do is complete the square, but what's wrong? I have an a term, so I need to divide everything by 4. So divide everything by 4 here, divide everything by 4 here. So I'm going to have x squared plus 4x minus 5 fourths equals, well, 0 divided by 4 is still just 0. Okay, so my b term is 4. B over 2 is 2. And b over 2 all squared is also 4. So I'm just going to have x squared plus 4x plus 4 minus 5 over 4, and what I do to one side, I do to the other. So I'm going to do that minus 4 and put it over here. Okay? So I'm going to rewrite this guy as the perfect square that it is. So it's just going to be x plus b over 2, which is 4, all squared, minus 5 fourths equals 4. Right? Then I'm going to add 5 over 4 on both sides. That's going to give me x plus 4 all squared is equal to, and let's go ahead and come up here and do that. So that's going to be 4 plus 5 over 4. That's going to be equal to 16 over 4 plus 5 over 4. That's going to give me 19 fourths. So I've got 19 fourths. Take the square root of both sides, and I'm going to have x plus 4 is equal to plus or minus the square root of 19 over 2, because the square root of 4 is 2. So that means I have rational solutions, because I didn't have to rationalize my denominator anywhere. Subtract 4 on both sides. X is equal to negative 4 plus or minus the square root of 19 over 2. So that means that my two rational solutions are x1 equals negative 4 plus square root of 19 over 2, and x2 is equal to negative 4 minus the square root of 19 over 2. Easy peasy so far. So 2 more examples. And if you've already got the hang of this, I mean, you don't need to watch everything on this video, right? You can watch the examples. You don't need to watch every single one, but it's a good idea to do so because there may be something included that you may need to see. 5x squared minus 30x equals 3. Let's just complete the square. Actually, well, we can't because we have an a term, so we need to divide by 5 on both sides. So that's going to get us to x squared minus 6x equals 3/5. Now we can complete the square. B is equal to negative 6. That's important. It's not positive this time, which means b over 2 is equal to negative 3. And b over 2 all squared is still just positive 9, because negative 3 times negative 3 is still positive 9. That's going to give me x squared minus 6x plus 9 is equal to 3/5, also plus 9. Again, I can't just add something out of nowhere. So if I did it to one side, I have to do to the other, or you can think of it another way. And I'll go ahead and do it that other way. I don't like doing it this way, but just so you can see. So plus 9 minus 9 equals 3/5. So I effectively added 0, right? So group and factor, this is a perfect square, meaning it's going to be x plus b over 2. Oops. X plus b over 2 all squared. So that means b over 2 all squared. So that's going to be x minus 3 all squared, not x plus 3, right? Why would it not be x plus 3? Well, because b over 2 is negative 3. All right. And minus 9 equals 3/5. Add 9 to both sides. X minus 3 all squared is equal to, so I'm going to add 9 to 3/5. That's going to be 3 over 5 plus 45. Whoa, that should be a plus, not an equals. Plus 45 over 5, because that's equal to 9. And we're going to get 48 over 5. Okay, take the square root of both sides. We're going to get x minus 3 is equal to the square root of 48, well, plus or minus the square root of 48 over the square root of 5. And let's come over here. So we've got x minus 3 is equal to plus or minus the square root of 48 over the square root of 5. Add 3 to both sides. Oops. And we can simplify, so square root of 48, that's equal to the square root of 16 times the square root of 3, which is equal to 4 square root of 3. And again, this right here means that our solutions are irrational. Okay, so I'm going to have to rationalize 3 plus or minus. That's going to be 4 square root of 15 over 5. Okay, so that means my two irrational solutions, x1 is equal to 3 plus 4 square root of 3 over 5. x2 is equal to 3 minus 4 square root of 3 over 5. Right? One more example. And then I'm going to show you what you can do for extra credit. See if any of y'all can figure it out. Okay. Number 4, 2x squared minus 6x minus 1 equals 0. So we got to divide everything by 2. Because we don't want that guy there. So we're going to have x squared minus 3x minus 1/2 equals 0 divided by 2, which is 0. Complete the square, so b equals negative 3. B over 2 is equal to negative 3 over 2. That's brutal. We got a fraction. And b over 2 all squared is equal to positive 9 over 4, because negative 3 over 2 squared, right? That would just be this. Okay, so to complete the square, that's what I'm going to have to do. I'm going to have x squared minus, whoops, what am I doing? X squared minus 3x plus 9 over 4 minus 9 over 4, because I'm adding 0, minus 1/2 equals 0. And again, you don't have to have done it that way. You could have treated it, it is an equation. So you could also do it this way. You could also say minus 1/2 is equal to, so I added 9/4 to both sides. It's the exact same thing. Okay, and this is actually going to save you a little bit of time. Then we just group and factor. And this guy is the perfect square. X minus 3 over 2 all squared minus 1/2 equals 9/4. Add 1/2 to both sides. Okay, and this is going to be the same thing as brain for it. 4 over, no. What's the matter with me? This is going to be the same thing as 2 over 4 plus 9 over 4. So that's going to simplify down into 11 over 4. And take the square root of both sides. And we get square root of 11 over 2. So this means our solutions are rational, right? We still need to get rid of that minus 3 over 2. Add that to both sides. X is equal to 3 over 2 plus or minus the square root of 11 over 2. So our two rational solutions, x1 is equal to 3 halves plus square root of 11 over 2, right? And we can actually go and take that a little bit further. So x1 we could also say is 3 plus square root of 11 over 2. So all of that's over 2 because they have a common denominator. And we can go ahead and get cute with that, which means that x2 is equal to 3 minus the square root of 11 all over 2. Right? And they, again, are rational, right? Because we didn't have to do any rationalization. Okay, so let me pull up your extra credit. And here it is. Okay, so basically here is the problem that you're going to solve. So number 1, 2, and 3 for extra credit. You have until Friday. That is, so what day is Friday? I'm having a brain fart. Friday is the 30th, day before Halloween. Okay, this will be 10 points, extra credit on our first test. Okay, and when you email your solution to me, either to me or Miss Roundtree, your subject needs to be exactly this. Otherwise, we're not going to take it. Your subject will just be EC Unit 2, Test 2. We'll keep it simple. EC Unit 2, Test 2. No, I'm an idiot. That should be Test 1. What's the matter with me? Sorry, guys, I'm tired. EC Unit 2, Test 1. Okay, this is your subject. Your subject needs to be titled exactly like this, or else you got to understand, me and Miss Roundtree get a million emails every day. If your subject isn't more or less exactly like this, we're not going to be able to find your extra credit, okay? So you got until Friday to get that done. Here's our EQs again, and that's all I got for you, children. Let me know if you have any questions, and obviously come to tutoring. Goodbye.